Hello everybody, welcome to another video lesson. We are continuing our complex numbers in polar form. However, we are going to now do some operations. We are going to be able to find products, quotients, powers, and roots of complex numbers in polar form at the end of this video. So let's hop right into our concepts. Now we had z equals a complex number, right? So z is representing a complex number in polar form. So now I have two different complex numbers, z1 and z2. So consider this situation here. We're going to find the quotient of the two. So let's find z1 over z2. So that is going to be r1 cis theta 1 over r2 cis theta 2, right? So in order to kind of solve this and simplify it a bit, let's go ahead and take the conjugate of my denominator, because I have this imaginary number down here, right? So if I do that, that would be multiplying by cosine theta 2 minus I sine theta 2 on both the top and bottom, right? That is the conjugate of the parentheses in the denominator. So then we can go ahead and expand this out. We get to this kind of crazy looking ratio here. But all this is we've just gone ahead and foiled our numerator and then our denominator as well just reduces to a squared minus b squared, right? So it's going to be cosine squared theta 2 minus I squared sine squared theta 2 right here in my denominator. Now we know what I squared is. That is just -1, right? So my denominator is actually going to simplify to cosine squared theta 2 plus sine squared theta 2, which we know simplifies to 1, right? So since that simplifies to 1, we can go ahead and just work with our denominator. Now we're going to go ahead and start grouping some things together. I'm going to group this cosine theta 1, cosine theta 2, and this sine theta 1, sine theta 2 together. And then I'll group my terms that have an I in them, combining those terms with an I. Now with that, again, my R's are it's just the quotient of our R values or our moduli. Moduli is the plural of modulus, which is our R values. So we have this R1 over R2, just kind of following along for the ride at this point. All right, so let's go ahead and get a clean slide up here, and we have the term that we had on the bottom of the last slide. Now, you may not recognize this, maybe some of you do, but our difference identity for cosine is actually what we have in this parentheses right here. So cosine theta 1, cosine theta 2 plus sine theta 1, sine theta 2 actually reduces to cosine theta 1 minus theta 2. Okay, this whole thing would be in parentheses right here, like that. Okay, so that is our difference ID for cosine, and we also have the difference ID for sine here on the right side in this parentheses. So this will be sine theta 1 minus theta 2 is what this reduces down to. So what we're left with is z1 over z2, so the quotient of these two complex numbers is going to be r1 divided by r2 times, this should be in parentheses, cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. And that is our quotient formula, is how we refer to that. Now, likewise, we also have a formula for the product. We call this our product formula of two complex numbers in polar form. So again, we've got some parentheses here and here. So that is going to be our moduli, the product of our moduli, times cosine theta 1 plus theta 2 plus I cosine theta 1 plus theta 2. Now, we are not going to prove that in this video for time's sake, but you might be asked to prove that in the future. So maybe take a look at that on your own. So these are going to be our two formulas that we need to write down and fully understand. All right, next concept, this thing called DeMoivre's theorem, okay? DeMoivre's theorem is how we say that. So now we've got z is equal to some complex number in polar form. Now what happens if I were to multiply z by z? So now using that product formula that we had earlier, I would have r times r times cosine of theta 1 plus theta 2, but my theta 1 and theta 2 are the same theta. Okay, so that's just going to be sine and cosine of now what? Of 2 theta, right? So I've got r squared cosine 2 theta plus I sine 2 theta. Now what if I go ahead and use this and say what is z squared times another z? Well, that's going to be z cubed, right? So again, I'm going to multiply my moduli. So I multiply r squared times r. And then I've got cosine of 2 theta plus theta and sine 2 theta plus theta. So again, since theta is the same, that's going to reduce down to r cubed cosine 3 theta plus I sine 3 theta. So in general terms, we would have z raised to the nth power is going to equal r raised to the nth power times cosine of n theta plus I sine of n theta. So that is our DeMoivre's theorem, and that is how we kind of derive it. Now let's take a look at our distinct roots. So we know any expression, right, with raised to, say, the p power, okay, we're going to call it the p power. So say it's raised to the 4th power. Okay, any function raised to the 4th power we know has exactly 4 roots, right? Now it doesn't have to be 4 real roots, but it does have to have 4 roots. So we can use our DeMoivre's theorem, and that's going to lead us to this expression right here. Now we're not going to prove this in this lesson. However, this is the expression that we would use to calculate the roots, all of the roots of a non-zero complex number. So say we were asked to find the 4th roots of some expression. We would go ahead and say p is equal to 4. So p would be 4, 4, and 4 here. And then n is kind of our dummy variable. We would go ahead and use this as our counter. So first we would plug in n as 0, then 1, then 2, then 3, and then we would want to stop at 3 because we always want to stop at p minus 1. So if we're looking for the 4th root, then p is 4, and so we would look at n equals 0, 1, 2, and 3, and then we can stop. Now if you forget to stop, that's okay. You'll just notice that the roots will start to repeat once n is greater than or equal to our p value. So if you keep going and calculate when n is 4, you're going to get the same root that you calculated when you plugged in 0. Okay, so that is finding distinct roots of our complex numbers. So let's go ahead and get into our examples. First one, we're going to find the product of these complex numbers. So we can just go ahead and use our product formula. That's going to be r1 squared cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And we've got our r1 is 3, r2 is 5, theta 1 is pi over 3, and theta 2 is pi over 4. So we can go ahead and plug those values right in, and we can calculate what pi over 4 plus pi over 3 is. That's going to be 7 pi over 12. This is going to be a 12 here. We're missing a 1. So that's 12. And that is 15 cosine of 7 pi over 12 plus I sine 7 pi over 12. And it asks us also to express this product in rectangular form. So in order to do that, all we would need to do is calculate the cosine and sine values, and then we would distribute our 15 through. So that's going to give us negative 3.882 plus 14.489 I. Okay, so that would be our complex number product in rectangular form. You guys go ahead and pause the video and see if you can't do the same with the product of these two complex numbers in polar form. You're going to express them both in polar and rectangular form. All right, hopefully you got these answers right here. And if so, I'll go ahead and move on to example 2. Example 2, we have a circuit with a voltage E of 100 volts and an impedance of Z. Okay, that's going to be 4 minus 3J ohms. Again, J here is just another representation of an imaginary number, right? It's kind of like I. Okay, we can also see that written as J. Find the current I in the circuit in rectangular form. We're going to be using E is equal to IZ. So we solve that for I. That's going to be I is equal to E over Z. And I'm going to write E and Z both in complex form. So 100 volts would just be 100 plus 0I. And then z we would go ahead and write as, we were given z already in complex form, so that's fine, rectangular form. So we can find out our r value now of z, because we want to put this in polar form. Okay, we want to put this in polar form, so find our r value. That's going to be the square root of 16 plus 9, which is 5. And then we need to find theta as well, so that's going to be theta is equal to inverse tangent of negative 3 over 4. Now we do have a negative b value, but our a value is positive, so we don't have to add pi to that. So that's going to be approximately negative 0.6435. And we would write e as 100 cosine 0. Again, thinking of this on a number line, okay, e would be just 100 and 0i. So it's just going to be only on the real axis. Only on the real axis. So that means that our angle would be 0, right? So we have 100 cosine 0 plus I sine 0. And then for z, we have 5 cosine plus I sine of this negative 0.6435. Let's go ahead and take the quotient of both of these. And then our quotient formula tells us that we take the quotient of the moduli, and then we subtract our theta values. And we can go ahead and start simplifying this down. And then we put this in rectangular form. It's going to look like 16 plus 12i. And those are rounded numbers. All right, let's go ahead and take a look at using our DeMoivre's theorem. We're going to call this DMT also, because this DeMoivre is a little bit tough to pronounce sometimes. So we'll call this DMT. Okay. Let's go ahead and find our power and express it in rectangular form. So we have our complex number 1 plus root 3i raised to the 4th power. So it's raised to the 4th power. We're going to go ahead and use r raised to the n cosine n theta plus I sine n theta. I know that z, my actual complex number, is going to be just what's inside my parentheses here, right? So my r value would be the square root of 1 plus 3, which is going to be 2. And my theta value is going to be the inverse tangent of root 3 over 1, which is just pi over 3. So my n is 4. We can go ahead and just start plugging these values in. So I'd have r raised to the 4th, so 2 to the 4th, cosine of 4 pi over 3. Times I, or plus I sine of 4 pi over 3. And we can go ahead and start reducing these down. We'll have 16, the cosine 4 pi over 3 plus I sine 4 pi over 3. That's going to be 16 times negative 1/2 minus root 3 over 2i. And that's going to give us a final rectangular form of negative 8 minus 8 root 3i. All right, so you guys go ahead, pause the video, and do the same thing for this complex number here. Find the power, express it in rectangular form. Alrighty, here's our process. Hopefully you got is very large numbers, negative 32,768 and plus 32,768 root 3i. Alrighty, last example here. Let's take a look at our roots, okay? Finding the cubed roots of 2 plus 2i. So again, we're going to use this statement here. We've got r raised to the 1 over p times cosine of theta plus 2n pi over p plus I sine theta of plus 2n pi over p. Okay, a lot going on here for this one. Now our p value, since we're looking for the cube root, is going to just be 3. Okay, since we're looking for the cube root, p is just 3. So our r value we need to find, which is going to be the square root of 2 squared plus 2 squared. So that's going to be the square root of 8. Now inverse tangent of 2 over 2, that's just going to be pi over 4. So we can just plug these in now. Okay, so I've got square root of 8 raised to the 1 over 3 power times cosine of pi over 4 plus 2n pi over 3. And let's see, we can simplify this a bit, and we're going to just kind of break these up. So now I've got the 6th root of 8 times the cosine of pi over 12 plus 2n pi over 3 plus I sine of pi over 12 plus 2n pi over 3. And now we can just plug in our n values. And since we are looking for the cubed root, I'm just going to look at n values of 0, 1, and 2. This needs to be an integer. N is always an integer. So starting at 0, 1, 2, and so on. And we want to stop at p minus 1, which in this case is 3. So let's go ahead and plug in n equals 0. So I'll have the sixth root of 8 times the cosine of pi over 12 plus 0. Likewise with our I sine term. And that is going to give us 1.366 plus 0.366i. Just plugging in those values and finding decimal approximations. Okay? And then we can find when n is 1, so I'll have the sixth root of 8 times the cosine of pi over 12 plus 2 pi over 3 plus I sine pi over 12 plus 2 pi over 3. And we calculate those values just with our calculator. We are going to get -1 plus 1i. And lastly, we'll go ahead and plug in n is equal to 2. So I've got the sixth root of 8 times the cosine of pi over 12 plus 4 pi over 3 plus I sine pi over 12 plus 4 pi over 3. So all we're doing, we plugged in 0 and then 1 and then 2 right here for this n value and then calculated our roots. So we have our 3 roots with good decimal approximations here. Now, sorry, I lied. I told you guys this was the last example. But it's not. We have one more, and that is just when we're finding roots of unity. Roots of unity. When you see unity, we're thinking 1, right? Uni 1, okay? So that means that my R value, or my modulus, is 1, which means we're finding roots really on a unit circle. So if I go ahead and find my R value, that's just going to be square root of 1, which is 1, and my theta is 0. Okay, so I'm starting off with this value of 1, 0. Okay, 1, 0. So it's on my horizontal axis here, 1, 0. And my theta is 0. So that is going to be 1 cosine 0 plus I sine 0. So that is how we would express this as a complex number in polar form, right? Now, if I were to go ahead and find the cube roots, again, my p value is 3. So we would say 1 raised to any power now is 1, right? So our modulus in this case is always 1. So anytime you see roots of unity, you know that your modulus is always going to be 1. So we'll go ahead and using our formula, I'll have always 1 times cosine of 0 plus 2n pi over 3 plus I sine 0 2n pi over 3. We can get rid of that 0 there, and that's just going to be cosine 2n pi over 3 plus I sine 2n pi over 3. And we do the same thing, plugging in n values of 0, 1, and 2. So when I plug in 0, I get a value of 1. When I plug in n is equal to 1, I get a complex number of -1/2 plus root 3 over 2i. And then when I plug in 2 now, that's going to be cosine and sine of 4 pi over 3. So I'll have -1/3 plus root 3 over 2i. And this 3 should actually, this shouldn't be 1/3, this should be a 2, right? So this is -1/2 minus root 3 over 2i. So those would be our 3 roots of unity. Now notice if I were to graph these in my Argand plane, what we get are these roots that are evenly spaced out across my circle. Okay, so we're not exactly finding roots where we're crossing the real axis in this sense. Instead, we are finding these roots that are evenly placed throughout my circle. Okay, and you'll find that if you have cubed roots, fourth roots, fifth roots, they're going to be evenly placed throughout your circle. All right. So that is it, guys. Now that is our last example. Good luck with your practice.